Okay, good morning everybody. So let's continue. So there is, I have announced the assignment. So I want you, so the handwritten digit recognition, you are supposed to first use the naive Bayes classifier which is given as part of the sklearn kit. You can use that first, and then for extra credits you may want to implement it yourself. So that is the reason why it's defined, why I have announced like that. So I will share an Excel sheet where you should enter your group ID. So your group ID is like, if you have 5 people, so you just take first two letters of everybody's first name and come up with the ID, and that ID everyone uses. Okay, so UG groups should be up to size 5, and PG groups should be up to size 3. Okay, and yeah, so this is one, and lab assignment 1 is out. Okay, so I will be giving every week lab assignments, and there will be roughly 10 days for each lab assignment, but the deadlines will be overlapping. Okay, so I hope you understand what that means. If I yeah, so we don't have like 10 disjoint intervals of 10 assignments. If I do, it will be 3 months. That cannot be it. So it has to be done in an overlapping way. Okay. Okay, so that is about all the announcements. So we were discussing estimators, and we looked at maximum likelihood estimators. So a brief recap. So an estimator is called as unbiased when you have the property that expected value of theta n uh, is equal to theta. Okay, and it is called as consistent when theta n goes to theta in probability. Somebody says saying something. Yeah, the lecture is being recorded, but I don't know whether it will come or not, but it's being recorded. Okay. So yeah, so this is called as consistent, and consistence is a convergence in probability. So what that means is, for all epsilon greater than 0, if I look at the probability of error. Okay, so this is a function of n, right? Remember, so there is, like, depending upon n you can have different estimators. So the probability that you make an error more than the epsilon threshold that you determined is going to go to 0 as n tends to infinity, no matter what level of accuracy you want. Okay, so this is going to be always true. Then we saw maximum likelihood estimators for two class of problems. We saw for multinomial. Okay, so in multinomial, what is the problem? So you are given data xi. Okay, I equal to 1 to n. This is your data set, and each xi can come from one of m classes, m or k, or I don't know what I used, but some one of m classes, and you would like to come up with the probability which governs it. So probability that xi is equal to 1 is pi, and I want an estimator for pi's. Okay, so just to refresh your memory, so suppose we looked at some example just to remind you. This is a kind of an important construction that keeps coming everywhere. So your data, suppose, is 1 2 2 1 5, let's say, like this. Okay, so what we do first is we transform it into vector notation, all zeros. And then like this. So each entry, so for like this when we have, so if you take the ith entry, it is xi, right? Ith entry is xi will have values for each position. So this is 0 1 2 3 like this till capital M. So xi jth entry, I'll put as this one. Sometimes I don't know whether I put it last time, but the purpose is to just say it's not exponential. Okay, I'm not taking the exponentiation. So this is equal to 1 if xi is equal to j, right? 0 otherwise. So that is a, I mean, this might confuse you. If ith observation is j, right? So this is something like this, and we did this transformation, and so some things that all of you may be able to understand. So what is summation xij for if I take sum over all j?
Number of times jth entry is seen. So.
Yes, I wanted you to make that error. That is not correct. Anyone else wants to try? Good. I mean, I want you to make. Yeah, it is 1. Is it clear, Sneha? I mean, I'm summing over j, right?
Yes, sir. Yes.
Okay, so what you were saying is this. If I sum over I, this will I going from 1 to n. So this is like total number of times, like whatever you said, total number of times j occurs. Okay, so we saw these things, and then if I sum over all, what it will be? If I sum over all, yes,
capital N.
capital N. So I see here I have used small n, capital, but I hope you don't get lost. If I am not doing the notations consistently, you have two choices: either understand what I meant, or you ask if there is something inconsistent. Okay, so that way we can address that. Okay, so we saw this, and what was the use of this transformation? The use of this transformation is we will now be able to write the likelihood. So likelihood of seeing of a particular parameter p for the data set that we just saw. Okay, this d you may or may not put, that is not necessary. So this is equal to what is the probability of seeing the data when your parameters are this p, right? So this we said is product over all I equal to 1 to capital N, j equal to 1 to capital M. Okay, so pi to the, so what is this? Pi to the power of x I j. Okay, and we could take the log, and that will give us double summation ln pi. Okay, and then I told you how we can use optimization to solve it. So what we do, yeah, so for those of you who are actually going to credit optimization, you are going to see many more examples from machine learning, and you will also see why this particular procedure is true. But for this course, I will not be able to tell you why this procedure is true, but you will eventually discover if you have done optimization. Anyway, so p of mu, right? So what we do is we write this like this. And then plus mu times summation 1 minus 1 minus summation pi. Okay, so then we try to solve this as a unconstrained problem, right? So because why did we do this? Because we wanted to maximize for with p small l of p, but such that summation pi is equal to 1. So we had this constraint, so Because there was constraints, we cannot use regular optimization by taking the derivatives. So we have to do what is called as Lagrangian. So this is called as Lagrangian. This particular mu is called as Lagrange multiplier. Okay, so I want you to like always think about why we talked about these estimators, right? So the purpose is this, right? So you had the base classifier. See, why did we talk about estimators? So the reason is you had base classifier which had priors, you had class conditional densities, then you had the loss function, and then finally with all of this put together we got the base classifier. Okay, so I will give you a homework. So I mean, since we can't cover everything that is possible, you can refer my previous year's videos, but homework for you is for a general loss function. Okay, please yeah, so arrive at base classifier for a general loss function. Okay, so this is a homework for you. So this is not an assignment, you don't need to turn it to me, but you need to know how to solve this. So whenever I talk about some homework, there's a good chance that I may or may not give it in midterm, right? I may give it in midterm if I remember. So yeah, so you can go back and do it. For a general loss function, what is a general loss function? General loss function is a function L from your actions cross the actual label y to r. So you have to look at the risk of a classifier, right? So this is the risk. Okay, so we can say this is r of h of x. This is the risk of a particular classifier, and remember h star of x, or maybe if I want to say, let's just be clear, hb, a naive base, sorry, a base classifier, right? hb hb of x is argmin over h, r of h of x, right? So the homework is to arrive at this. Okay, so coming back, so you had priors and you had class conditional densities and then you are given a loss functions, you arrive at base classifier, right? So this was how we came up with base classifier, and this base classifier you'll deploy it in real world, and you will see its performance and all those things, right? But what is the problem? I mean, what is the issue here? Can someone tell me? I mean, there is a clear glaring error. If you have to use this in real life, what is the problem?
We need good estimators for.
Yeah, we need estimators, right? We need estimators. We need good estimators for all these things, right? For priors and for even class conditional densities, or sometimes which are also called as likelihood. So we need good estimators for these quantities. And since we need good estimators, but we are given data, the question that we were trying to address is that, so see, if you are given the probabilistic model, okay, you can draw IID samples and you can get your data set D, right? You can IID samples, you have data set which is Xi or Yi, you can get this. Okay, this is one problem, but the other problem is if you are given Xi, Yi and you are supposed to estimate the probabilistic model, right? So this is where MLE will come into picture. Okay, so that is why we did this. Okay, so this is one homework. Then I will also give you one more homework. So Okay, so the point is this. Okay, so if I find that there is a lot of participation in the class, I will try to cover most of it in the class. If people are quiet, you will lose out in your participation mark, obviously, and also you will get more homework. So one more homework is this. So this is a little bit more elaborate, but there is a topic called as Bayesian estimations, Bayesian estimators. Okay. So there are things which are called as maximum a priori, or which are called as map estimators. Okay, and then mode of the posterior. These are all various types of Bayesian estimators. Okay, so I will leave you to go and read this. Okay, so you can find this. You just look at the index for map in maybe one of the standard textbooks, or you can look at some lecture notes or my previous year videos. So you will find all these things. So I will try to give you links to my previous lectures, year's lecture, and you can see these topics. Okay, so so I hope at least the context of why the estimators are coming is clear to everybody. So are there any questions so far? Okay. All right. So then let's move on to the next topic. It's also a related topic to this Bayes classifier. So see, but let me say like this. So we had this problem of credit default, right? So what we looked at credit default is we try to predict whether if someone is given a loan, whether they will default or not. And the feature that we looked at was XI, which is basically tax paid date minus reference date. Okay. So basically, and then we assumed that the class conditional densities F0 and F1 had very distinct features like this. Okay, something like this. And then we did the Bayes classifier with all these assumptions. This is what we did previously. So of course you had the priors as well, but that is anyway easy thing to estimate, right? So we had something like this. But now let's look at F0. Okay, so suppose we focus on F0. So these are people who don't who don't default, who pay actually taxes early and who don't default on the loan, right? So here we can think of the entire population as coming from two types of individuals. Okay, so let us assume that there is low income group and high income group. There are two groups of people, low income group or high income group. We are looking at only those people who are not defaulting. Okay, even those people who don't default can be thought of as coming as from low income group or high income group, but we don't know the feature. I mean, we don't really know whether somebody is low income group or high income group. All we know that there are people from low income group. We know that there are people from high income group, right? So if you look at this particular feature, we assumed that this entire thing was normal with the mean minus 1 1, something like this we assumed, right? So this was mean minus 1 and some variance 1. But consider the alternate way of thinking about this. Okay, so depending upon whether somebody is low income group or high income group, we can think. So if I look at F0 of low income group people, okay, F0 comma low income group of X, if I look at this, so this may be not necessarily normal with mean minus 1, but it could be something like normal with mean 0. Okay, they are paying the time, they are paying their taxes on time more or less, but they don't pay as early as we thought they would. Okay, So this is the assumption. And then we also have for the high income group, we have this assumption. These people can afford to pay very early taxes, so this will be -2, right? So and further, let us assume that probability of seeing low income group is I don't know, maybe half the people are low income group and half the people are high income group, right? So if I put this together, all these things that I know, then F0 will be actually not a smooth normal distribution, but it will have something like this, right? Combination of two factors, isn't it? So there will be the low income group and the high income group. The low income group fellows will be on 0, this will be on -2, and this will be on -1, the mean of this. So this is considerably different from the assumption that we made of this, right? We made that assumption of this classifier, right? So this is what we thought originally we are using. This was original F0 of x, right? But I'm trying to say is like not everything in life has the smooth feature, which is it will not be nicely unimodal, nicely normal. Sometimes it will be a mixture of normals. Okay, so basically what I am saying is that pi 0 of x is pi low income group of F0 low income group of x plus pi high income group of F0 of high income group of x. Okay, so are there any questions so far?
Sir, what is this pi?
So pi is the probability of seeing. So this is the probability of low income group.
Okay.
Okay. So this is one example where you are getting what is called as Gaussian mixture models. So this is the example that I gave you is what is called as Gaussian mixture models, or what are called as GMMs. Okay, the procedure is same. Whenever you are given Gaussian mixture model, you have to estimate all of these parameters along with the see, if you had pure normal distribution, what you were supposed to estimate was P0, P1 and F0, F1. Now you have to estimate P0, P1, F0, F1, but in addition you need to estimate these quantities and these quantities. Okay, so basically the problem has become a little more richer. Okay, so this is one example where Gaussian mixture models are used. So Gaussian mixture models or GMMs are very popular. It has a lot of applications and it does really well as well. So yeah, so we will spend some time on Gaussian mixture models. So let's now focus. So we now understand the motivation, how it appears in Bayes classifier. Now let us focus on how to estimate so the problem is clear, right? So you are supposed to estimate given a Gaussian mixture model f of x, which is pi 0 f0 plus pi 1 f1, right? So you are given data from this model. So your data set is xi I equal to 1 to n. So my goal is to come up with theta MLE, which maximizes the likelihood of theta, where your data is coming from this underlying distribution. Okay, so we are supposed to all that we have seen so far is when you are given data set, how do you come up with, for a simple model we have seen how you can do maximum likelihood estimator, but now we are trying to do for a more complicated model, which is a mixture of two, but in general it could be mixture of k as well. So in general this is one way, but it could also be pi 1 f1 plus pi 2 f2 plus all the way till pi k fk. This also could be there, and you are supposed to find theta MLE for this problem as well. This also could be one such problem. So before we try to solve this problem of Gaussian mixture models. So let me introduce another example where Gaussian mixture models are useful. Okay. So Gaussian mixture models are also useful in an unsupervised setting. In an unsupervised learning setting. Okay. So there are applications for GMMs in unsupervised learning. So in particular, we will look at one most popular unsupervised learning algorithm, which is called as k-means. So this is where we will start from. Okay, and thereafter we will try to come up for the maximum likelihood estimator. How do you solve it for a general Gaussian mixture model? Okay, so is the plan clear? What we are planning to do?
Yes.
Yes, sir.
Okay, so yeah, so now let's try to understand what is called as k-means. So let us say you want to design a vending machine. Okay, so for vending machine, one of the things you should be able to do is to recognize different denomination coins, right? You should be able to distinguish various types of coins. Okay, so for example, you should be able to distinguish rupees 1 coin, rupees 5 coin, and rupees 10 coin, for example. Okay, so one way to do this is I will now measure two features. uh, x1 will be, let us say, diameter, and x2 will be, let us say, x2 of ith coin, right? Will be weight. So what I can do is I can collect several 1 rupees, several 5 rupees, several 10 rupees, and I can individually uh, measure the diameter, I can measure the weight, and I can do this for every single coin. Okay, and depending upon the manufacturing process, sometimes the diameter and sometimes the weight will change, right? So sometimes it will not be consistent. So means there will be a deviation. So you can think of uh, you can think that each of the coins will be having some mean and some distribution around the mean. Okay, the distribution around the mean, we can think of this as normal distribution. Okay, so this is one way you can do your learning problem, right? So approach one, I would say, not so smart. Okay, so maybe shall I say straightforward. So straightforward approach is like collect hundreds of coins of each denomination. Okay, then after that estimate priors, and then class conditional densities. Then third approach is you come up with a base classifier. This is approach one. So this is okay. It's a costly thing, because what you now need to do is you need to physically start collecting, right, and start measuring, right? And if you are just one person running this company, it will be a challenging task to measure all of this. Okay, so I mean, yeah, to label this, right? So this is this is coins is an example which is probably easy, but in general you may not have this easy problem, but you may have a many more features. So getting individual points classified by human expert is a challenging task. So instead, what you do is you put this, you collect a bunch of coins and put it through your vending machine, which can directly measure height and weight. Okay, so what you do is you don't care about what is the denomination. So we are talking about approach 2, which is clustering based labeling. So what we will do is we will get we will put the hardware ready for the vending machine which can measure these quantities. So we will measure the two axes will be height and weight, sorry, diameter and weight, and I will simply start measuring, right? So if the first coin is 1 rupee, so it doesn't have too much diameter, it doesn't have too much weight, so it will be here, right? And so this is my, let's say, diameter, and this is weight. So it doesn't have too much diameter, so it will be here. Second coin, when I run, perhaps it's also a 1 rupee, but we don't know that it is 1 rupee, so that also falls here. The next coin is, let's say, 5 rupees. It has roughly the same diameter, but the weight is considerably more, so you will have 5 rupees here. Then you will get a 10 rupee, which is having higher diameter, and the weight could be similar or maybe slightly less than 5 rupee, right? So you will have a point here. This is the 10 rupee, and you keep doing this, and then you will get a cloud of points. So this is how you will get, but you don't know that. I mean, now I am telling you, but you that this is 1, this is what is this? This is 5, and this is 10 rupees. I'm telling you, but in general you wouldn't know. But the points will just keep falling, and it will become like this. Now the idea is what we will try to do is we will try to group them like this. So you want to group these 3 into points like here. This will be one group, this will be another group, and this will be third group. Okay, so this is how you want to group it. This you want to do without knowing what the labels are, just based on height and weight you want to group it. Okay, once you group it, you will take one sample from each of them. So I will take one sample from here, and I will take a black sample from here, and a red sample from here. Okay, I will look at the blue sample since it is in this blue region, and I can look at it. So I can say, oh yeah, this is actually 1 rupee. So I will say this cluster is, so this cluster is rupees 1, right? And this cluster is rupees 5, and this is rupees 10. Okay, so that way I can come up with so here I had to label only a very few points. So if you are still not sure, you can do for a couple of more points in this group. You can do check for a couple of more points, check for a couple of more points. So this is much simpler than doing the labeling for every point, right? So is the difference clear? I mean, I have not told you how to do this grouping, but other than that, is the difference clear in the two approaches?
Yes, sir.
Sir, I totally get what gaming clustering is, but particularly for the example that you are mentioning, won't all the 5 rupees coin weight exactly the same and have the exactly same diameter since they are being manufactured in proper way?
Yeah. So so if that is the case, then we have like no variation. This will be a very tight cluster. Yeah, but yeah. So what you are saying is a much easier problem. For that, we don't even need to worry too much. Siddhant, I don't know whether I answered your
Yeah,
question.
I got it. Like maybe these are some other variations that come along.
Maybe it's not really the coin. The point is like you have data like this where there is variability. Yeah.
Yes, sir.
So yeah, so we will. I will give you an assignment anyway. I have an assignment planned for you, lab assignment for this particular clustering based labeling. I will give you that at some point, but you'll get to experiment with this. So nothing. Yeah. So other questions? How? I mean, I haven't told you what is k-means, but are you able to see the advantage of clustering?
Yes, sir.
So one more good thing about clustering is you can use this as dimensionality reduction. So another application of clustering is dimensionality reduction. Let me see if I can give an nice lab for you to check this. But this there is a dimensionality reduction things come. So what is the dimensionality reduction? So can someone tell me how the dimensionality has reduced in clustering?
Sir, in the normal Bayes approach, we had x1, x2, and y, but here we just have x1 and x2.
No, no. X1 and X2 and Y, correct. That is true. Why I'm not even thinking about. Let's say
Maybe
Maybe
because of
the
the
number
number
of
of
features.
clusters.
there are two people speaking. Someone.
Maybe because it depends more on the number of clusters, how many clusters are formed, instead
Yes.
of how many dimensions features we are
Yes,
using.
yes, very good. So there were actually two dimensions here, right? Height and weight. Now instead of doing height and weight, I am just having one indicator, whether it belongs to cluster 1, whether it belongs to cluster 2, or whether it belongs to cluster 3. See now, don't get confused about rupees 1, rupees 5, rupees 10, that business. That is put aside that. But see about this dimensionality problem again, right? So there were two dimensions where originally the data points were. Now I have changed from two dimensions and I have just made it into one dimension, which is the cluster center, right? Which cluster each point belongs to. So there is a dimension. So there is two only here, but there could be 100 dimensions, and I could have reduced from 100 to just one. Okay. So when we the advantage of dimensionality reduction, you will see when we come to the topic of uh, statistical learning theory, or when we do bias variance trade-off. We will come to these topics at some point. So you will understand what is the benefit of doing dimensionality reduction. Okay. So how this fits together is there are approaches, there are benefits of doing clustering on its own to for labeling for dimensionality reduction. There is also the application of clustering to try to do the Bayes classifier when your data is not purely normal but it is having some kind of multimodality. You can then possibly think of trying to represent this as combinations of various normals. Okay, so these are all the applications of using clustering, but the simplest clustering method that we will see first is what is called as k-means. Okay, so let's
Sir,
yeah,
in dimensionality reduction, like we reduce the dimension, so is there any loss of information?
there will be loss of information, but sometimes this having too many dimensions actually makes our learning algorithm overfit. Okay, so it is a trade-off. So sometimes so if you have too many features, your model can be potentially very complicated, right? You can have a very complicated functions that you can represent in this with multiple features. But what happens is when you have too many features, you will have the problem of overfitting. So we will see these things later, but yeah, you are right, there is a issue of loss.
Okay, thank you, sir.
Okay, so let's try to solve the k-means problem. How to do this k-means? So let's remove all these, right? So in the original problem, you don't know what are the groups, isn't it? So um, yeah, so I don't know anything, I just know the data. Input is my input is the data which is xi's, right? I equal to 1 to n. Each xi may be actually a vector which is xi1, xi2, like this. Okay, so yeah, you have something like this and you want to cluster it. So what is the meaning of cluster, and how good are two clusters? So let me make it more formal. So let's say I have let me ask this question to everybody. So let's say there are okay, maybe I'll just put a few more points. See, we are having same set of points, and let us suppose I cluster them in this way. One group is this, and another group, let us say, is this is one group. Let us say this is another group, and this is third group. Okay, so the grouping is what the clustering says, right? It doesn't tell you much more than that. I suppose I have one grouping, one is this, okay, another one is 1, 2 and 3. So there are these two different groupings that I am doing. So this is, let's say, grouping A, this is grouping B. So which grouping is better in the chat? Can you say A or B in the chat? Right, so it's pretty obvious that A is better. So how do you know A is better? Can someone tell, why do you think A is better?
Sir, because the points in the cluster, like the distance from the center of the circle is closest, like the points are closest.
Okay, so that is actually the reason. So what we will do is yeah, so basically what we need is we need like a measurement, or we need to define what is called as good cluster. Okay, so that is where we are headed. So what is a good cluster? If you want to define that, will answer whether A is better or B is better, right? So here is what I propose. So let us say I will define two things for each cluster. So first is what is called as cluster center. So we will define what is called as cluster centers. Okay, so or cluster centers we will define, or which are also called as centers or centroids. Okay, so this is let's say I will call them mu1, mu2, all the way till mu k, if I am interested to find k clusters. So this is the centroids. This is one thing. Second thing is I will also have yi j. Okay, so this will be 1 if ith point belongs to jth cluster. Okay, and I will define the cluster, the function which defines, so j of mu and y, okay, given a particular clustering, I will define this as 1 over n, total number of points, yes, Yij into distance between the ith point, I equal to 1 to n, j equal to 1 to k, right, k clusters, xi minus mu j. So I will try to find the distance like this. Okay, so is it clear what this is trying to do?
Can you repeat it, sir?
So Himanshu, tell me what is Yij?
Yij equals to 1 if ith data set is in jth cluster.
So for all of these points, suppose this is cluster 1, this is cluster 2, and this is cluster T. For all these points, what will be Yij? So what will be Yi1? What will be Yi1? For all these points, what will be Yi1?
It will be equal to 1.
It will be equal to 1, right? And for all these points, what will be Yi1? For all these
0.
points, yeah, for
0.
these points it will be 0, whereas Yi3 will be 1 for all these points, correct?
Yes.
So that is what is Yij. And what is mu j? Mu j is the center of each cluster. Okay, this is mu1, this is mu2, this is mu3. Okay.
Okay, yes, I get it.
So this is the distance. I am looking at the distance of every point from the corresponding cluster center. Okay, is this clear, Himanshu? Distance from the average is the lowest, more data points in the cluster. Okay, so what is this trying to do? It is trying to find out the average point, average distance from every point to its corresponding cluster. Okay, and the goal of k-means, goal of k-means is to do argmin, try to find that assignments which will minimize this. Okay, so you want to find out all those mu's and y's such that this is minimized. Okay, so are there any questions so far? I'm not able to understand. Is it clear?
So,
Yes. Yeah.
sir, we are measuring the variance, the variation with the help of Yij's, right?
Yij's
Like
is
the indicator function is,
yeah, indicator function is Yij.
yeah, yeah, the indicator function is in some sense helping us know if this belongs to this particular cluster or not,
Yes, that's all.
right?
That's all. Yeah.
Granting we have a particular shape, like a radius kind of a thing, that from the center of it, like from a particular mu k, we can have a particular radius, and if the point belongs to this particular radius, is lies within this thing, then it belongs to this cluster and not like.
Yeah, that is that's how it is coming, no? So you, for a new point, you see which is the closest, right? Suppose there is a new point here, you find out which is the closest. So if it is closest to this center, you assume that this belongs to this cluster. Otherwise you assume it belongs to this cluster, right? So for example, the point here will belong to this cluster.
But we are not having a very definite radius given to each cluster,
Yeah,
right?
because there will be outliers, no? Sometimes see, the points don't always neatly fall like this. There will be always some noise, and there will be points which are somewhere here. Sometimes there will be points which are nowhere, somewhere here, right? So there is no clear radius by which you can say. It's not like your like that coin problem where everything will be precisely manufactured. There will be variability, isn't it? And there will be not just 2 dimensions, there will be 100 dimensions. You cannot even visualize it. What you are trying to say is, can we come up with alternate ways to characterize how good a cluster is? That is what you are trying to answer in a different way. But I am saying, for a 2-dimension case, whatever you are saying is try to look at the radius, all that thing is fine. But if there is noise, that will not work. And plus, you still cannot tell how good it is. You have to look at all the points and how close they are to the center, right?
Okay.
Yeah. Okay, so let's stop here. So tomorrow I will explain more things about this. So we will stop here. So I will stand by. I will wait for if any questions are there. Okay. So yeah, thanks everyone.
Yeah, sir, can I ask just one more thing in a different sense?
Yeah. Just a minute. This tracker should. Okay, I don't know what is happening. Okay. Anyway. Yeah. So ask. What is the thing?
Yeah. Sir, we were discussing that there is some loss of information when we use k-means clustering,
Hmm.
right?
Hmm.
Can we use supervised data along with it? So, for example, if we have various kind of parameters, not just two, and
Hmm.
there are multiple of parameters like 18, 20 parameters which are being evaluated for k-means cluster,
Hmm.
right? Then it can create a chaos, something of that sort.
Yeah. So you have to be careful whenever you are doing clustering for dimensionality reduction. You have to see whether you are getting any benefit out of it or not, right? So,
Yeah. So, can we use some sense of supervised learning as well? Like if we have some knowledge
hmm.
that definitely if we are, let's say we are working on a data set of students
Hmm.
wherein this particular student will choose this particular branch, something of that sort,
Hmm. Hmm.
right? Aligning by their interest we can determine which branch they should go for or something of that sort. In
One
that
minute.
case we are
Let me just stop the recording because